Hi folks, Mr. Long here. I'm going to go through an example, the first example for graphing log functions. Okay, so this is that are transformed. So not just basic log functions like log of x to the base 4, but left-right translations and what I call scaling. Although we're going to do this without the standard transformation method. We're going to do it by making sure that we really understand logarithms. Okay, so the specific example that we're going to do is posted right here. Okay, this is the specific example right there. And so you can see, I'll zoom in on that so you can see it. That is negative 5 log of x base 3 plus 10. Right, so remember that the key things to remember as we work through this is that x is your evaluated power, that's your base, and f at x, or we're going to refer to that as y, that is your exponent. Okay, your exponent is over there. All right, so here we go. First thing we want to do, we've got like an algorithm, a step-by-step process here. The first thing we always want to do is to figure out if there's any reflections. Okay, so are there any reflections? And the way we do that is we look at the equation and we see, we look at could y be multiplied by a negative? And could x be multiplied by a negative, right? That's the big thing. So I'm going to look right here at this right here, and it looks to me like x cannot be multiplied, or x is not multiplied by a negative. So there's definitely no horizontal reflection. Okay, x is not being multiplied by a negative. Now, I don't see y over here because that means y equals, that's not being multiplied by a negative either. But what if I multiplied this side and this side both by negative 1? So I'm going to put here multiply by negative 1. Well, if I multiplied both sides by negative 1, I'd get a negative over here. I mean, that would become a positive and that would become a negative, but that's not what's important. What's important is, could y become negative? It could. If we multiply y by a negative, if we have negative y, then we have a vertical reflection. So this is the original curve, or what the basic log curve looks like this. But if there's a vertical reflection, it looks like this. Okay, that's a reflection over top of the x-axis. Okay, so this right here, I'll circle this one, this is what our curve looks like. Okay, so the general shape of the curve that we're going to sketch in this example is like that. Okay, so now we've got to look at the domain. Okay, so the domain and the vertical asymptote. Okay, and we do that with our evaluated power. So we've learned that the evaluated power is always greater than 0. There's no base that you can repeatedly multiply or divide where you get a 0 or a negative. It's just not possible. You can't multiply 5 over and over again or divide by 5 over and over again and get a negative. You can't, right? You just can't. And we only work with bases that are positive in high school math. And so the evaluated power always has to be greater than 0. Well, where do you see the evaluated power? The evaluated power is right there. It's just x in this case. That's all it is. So I know that x is greater than 0. Okay, and that gives me the domain. That's the set of x values that are allowed. But it also gives me something else. Since x is always greater than 0, I know that the vertical asymptote is at x equals 0. Okay, there's something else that I know. So now I know the vertical asymptote. I also know the domain. This right here, in this example, we don't have to do it. That will come later. Now we have to solve for the x-intercept. So how do we get the x-intercept? Well, we know the y value is always 0. Okay, the y value is always 0 at the x-intercept. So I can go back to this diagram actually, and I could say the x-intercept is going to be like right there, right? That's where the x-intercept is on the picture. So let's take a look though. Let's actually solve for that algebraically. So I have negative 5 log of x base 3 plus 10 equals 0. And that's the equation I need to solve. So how do we solve this? Well, I would subtract 10 on each side. Negative 5 log of x base 3 would equal negative 10. Now I need to right now a log is being multiplied by -5. The opposite of that is to divide by -5. So I would end up log of x base 3 would equal 2. -10 divided by -5 is 2. All right, so now this is b base evaluated power, and that's n the exponent. So I'm trying to figure out what the evaluated power is. That's going to equal the base to the exponent n equals the evaluated power. So I'm going to write that as 3 to the 2 equals 9. Okay, so I know that x equals 9 is the x-intercept. Okay, that's the x-intercept. Now, could have I done that without going through all that algebra, just by looking at the equation? Well, let's see if I could. So here's what I want to do here. I'm going to do this. If I highlight this, and I think of what that equation says. Okay, so what does that equation say? That equation says -5 multiplied by that plus 10 equals 0. So that means this has to be -10, both of those together, right? So -5 times something is -10. Well, what do I multiply -5 by to get 10? +2. Look at that. I need +2 for that exponent, that log. If the exponent is 2 and the base is 3, x has to be 9, right? So I could have looked at that and known that that was 9. But I think it's worthwhile going through the algebraic process. So now I know the x-intercept, I know the vertical asymptote, I can draw a sketch. Okay, I can definitely draw a sketch. So what will this sketch look like? Well, I know that the vertical asymptote is at x equals 0. I know the general shape of the graph is like that. I also know that the x-intercept is at 9. There's my x-intercept. Okay, I know that. So I already have the sketch. What I want to do is verify that my sketch is correct. And the way I'm going to suggest that you do that is you come up with a point up here and down here. Okay, and just get what those ordered pairs are. So you're going to get a point that's near the vertical asymptote. That's this one. Okay, you're going to get a point near the vertical asymptote, and then you're going to get a point for the end behavior, okay, way out here to the right. And so here's the way we do that. So the first thing I'm going to do is I'm going to check near the vertical asymptote. And what I'm going to do is I'm going to go 10 to the -4th of a unit away from the x-axis. So 10 to the -4th of the way from the x-axis. So what does that mean? Well, if it's 10 to the -4th away, that means I've got to sub an x value into the equation at 10 to the -4th. How do I do it? Well, the x value I'm going to sub in is going to be the x value of the vertical asymptote, and then I have to go to the right plus, and in this case, the base that I'm working with is 3 to the -4th. That's the x value I'm going to sub into the equation. So that's a distance that's really, really close to the vertical asymptote. And then I'm going to figure out the y value. So we know our equation is -5 log of x base 3 plus 10. Well, what is this? This is going to be 3 to the -4. And we know what exponent do I put on 3 to get 3 to the -4? What's -4? Right? It has to be -4. So this is going to equal -5 times -4 plus 10. That's 20 plus 10, which is 30. So y equals 30. Okay, remember you can pause or rewind this video at any time. So I'm going to go back up. And I know now that this ordered pair is at 10 to the negative 4, comma, 30. So like almost touching the y-axis, and then it's up at 30. So that makes sense. That should be up high, right? So it's going up the asymptote. Now this one here better have a negative y value, right? If we've done it correctly, because we're to the right of that x-intercept. Okay, and by the way, the distance we're going to go here from the vertical asymptote is 10 to the 4th units. So that's like, if it's base 3, that's 3 times 3 times 3 times 3, which is 3 cubed is 27, so that's 81 units away. Okay, so we're at x equals 81. So let's see here. So the x value I want to sub into the equation is the x value of the vertical asymptote, which is 0, plus 3 to the 4th. Okay, so what does y equal when x equals 3 to the 4th? Well, negative 5 log of x base 3 plus 10. I sub in that 3 to the 4th. And that makes life really good because log of 3 to the 4th to the base 3 is automatically 4. Hopefully you see why I'm using this in terms of exponents rather than actual x values. So negative 5, and this works out to 4. So negative 5 times 4, whoops, plus 10. Well, negative 5 times 4 is negative 20. Negative 20 plus 10 is negative 10. So I go down here, or go up to the graph rather, and I know that at 10 to the, well, not 10 to the 4th, sorry folks, 3 was our base. At 3 to the 4th, when x equals 3 to the 4th, y equals negative 10. Now, I know I went through that fairly fast, but what I would encourage you to do is to go over that, okay? Go over the process there. So all we're doing in this last step is verifying that our graph is accurate, okay? There's 2 test points. And the test point is one's really close to the vertical asymptote and one's really far from the vertical asymptote, okay? So 3 to the 4th units over to the right, which is 81. So we're always going to go to the 4th because that's a pretty big exponent. Okay, so 10 to the negative 4th away from the vertical asymptote because that's super close to the vertical asymptote. Oh, Mr. Long, Mr. Long, Mr. Long. That should have been 3, and that should have been 3 as well. We're working with base 3. My apologies. Okay, so I now have my test points done. I have my x-intercept done. I have my vertical asymptote done. And I've got my end behavior. Okay, so that's it, folks. Please, again, rewind, watch it again. I would do this example even on your own after you've watched this. Have a great day.